This video is a continuation of our 6.3c lesson, Applications of the Area of a Circle. So we're picking up on number 7, and it says the point 30 lies on a circle with the center at the origin. Remember that origin means right at 0, 0 in the middle. What's the area of the circle to the nearest hundredth? And then it tells us as a hint to sketch a coordinate plane. So that's what I did over here. I sketched a coordinate plane. And I put point 30 right over here and then the origin. So if I have a circle, that circle is going to go equidistance all the way around back to where we started. So that means that my radius from here to here is actually 3 units. I have to count over 3 to get to 30. So I can start with my area formula, area equals pi r squared. And I'm going to substitute in the 3 for my area. So my exact answer would be 9 pi, but this problem tells me to do an approximation. So I'm going to substitute in the 3.14 and multiply that out, and I get 28.26 units squared. And I can enter in a sentence, therefore, the area of the circle is about 26.26 units squared. And I'm using that word about because remember it was an approximation because we used the 3.14. All right, number 8, a radio station broadcasts a signal over an area with a radius of 50 miles. So if I start sketching, here's that broadcast area with a radius of 50 miles. The station can relay the signal and broadcast over an area with a radius of 75 miles. So with a relay, we can go even bigger, and this can be with a radius of 75 miles. How much greater is the area of the broadcast region when the signal is relayed? Round your answer to the nearest square miles. So we're looking for the nearest whole number. Now this is very similar to the problem that we did with the pond and the walk. So I'm going to have you try this one on your own. Hit pause, give it a try. When you're ready to take a look at your answer, hit play. Okay, let's see how you did. So I took the area of the relay with pi r squared, and I used the 75 for the radius, and then I subtracted out the without a relay. That's going to leave that whole extra ring of extra. Now, when we did this with the pond and the walk, we wrote it as 2 separate problems. You're going to notice on this one, I combined them and did them both sort of at the same time, which is totally fine. Let's take a look at number 9. Number 9 says to determine the area of the shaded region in each of the following figures. So I'm looking for the shaded part. Now, can we use a similar strategy to what we were doing with the pond and the walk example with this square and a circle? Absolutely. We can think of finding the area of the entire square and then subtracting out the circle, and then that would leave us with the area just in the corners. Now, if I know that the radius here is 5, then all the way across from the top to the bottom, I'm going to get 10 inches because 2 radii make the diameter, which is the length of the side of the square. So area equals, and I'm going to use base times height for the area formula for my square, minus the circle, pi r squared. So area equals 10 times 10 minus the pi times 5 squared. So area equals 100 minus 25 pi. Now, if they asked me for an exact answer or an answer in terms of pi, that's what my exact answer would be. But my directions tell me to round to the nearest hundredth. So I'm going to put in an approximation. So 25 times the 3.14. So area is approximately that 100 from the square minus the 78.5, multiplying that out, and I get that the area is 21.5 inches squared. All right, let's look at B. We have a couple different ways that we could try tackling B. We have these 4 circles, and we want just sort of that diamond area in the middle. Now, play around with this a little bit and see if you can find another strategy to solve this. But one way that we could do it is if this is 1 inch, then I know from here to here is also 1 inch, and from here to here is 1 inch. Then if I continue down into my next circle, another inch and another inch. So all of this right here would be 2 inches. And I can continue connecting all of the centers of my circle, and I see that I have a square, and inside that square I have 4 quarters of a circle. So if I found the area of this entire square and took out a circle, I would be left with the shaded area in the middle. Now again, there's more than one way to solve that, so put on your creative hat and see if you can find another way to do it. So I have my square minus my circle. Area equals, remember, that's 1 inch and another inch, so a 2 by 2 minus pi times 1 squared. That becomes 4 minus pi. And again, that would be my exact answer, my answer in terms of pi, but it told me to estimate or to approximate. So 4 minus and then 3.14. Let's make that approximate. So is approximately 0.86 inches squared. All right, let's flip the page. On the next page, we have 4 figures, and it tells us that they're all squares with a side length of 2x. So from here to here would be 2x. Which figure has the largest shaded region? So we want to find the area for these 4 and then do a little comparison. Well, let's think about the radius for each of these circles. So if I know that up and down that whole way is 2x, then if I find just the radius, I have x. Now I know that from here to here, again, is 2x. That also happens to be the radius of that whole big circle. I just have a quarter of it, so I'd have to multiply the whole thing by a quarter. Now on this one, again, the whole thing is 2x, so the radius would just be x. And again, the whole thing is 2x, so the radius would be x. So what I'd like you to do is, using your formula, area equals pi r squared, find the area of these 4 circles and then compare and tell me which one has the largest shaded region. Hit pause now and give it a try. All right, so we have now found the area of the 4 different shaded regions, and what do we notice? They're all the same. Absolutely, and if we look at their radius, we can actually see those 3, the first one and the last 2, have all the same radii. So we see that all 4 figures have the same shaded region. So they all look very different, but they're going to take up the same amount of space within that box. All right, number 11. How does the area of a circle change as the radius is multiplied by a factor of n, where n is a whole number? So this is going back to our rules of scale factor. If I were to multiply it by 2, my area would have a scale factor of 2 squared, or 4. If I multiplied it by 8, then my scale factor area would be 8 squared, or 64. So if I don't know what the number is that I'm increasing it by, I do know that I have to square it. So the area will be multiplied by n squared. Whatever that n is, if it's doubled or quadrupled or times 8, we'll then square it. All right, looking at number 12. An archery target consists of 5 concentric circles. That means circles right in the middle of each other. Points for each region on the target are indicated. The radius of the bullseye is 4.5 inches. So that's right here in the middle. Right there is 4.5 inches. Each ring surrounding it is 4.625. So from here to here, not going all the way in, but just from here to here is 4.625 inches. So it's going to ask us to find the area of the bullseye. And then on the next page, what's the area of the 7-point region? So we're thinking this area right here. Okay, and then what's the area of the entire target? So we're thinking all of this. All right, so I want you to take a moment and do part A, B, and C on your own, and then check back and see how you did. Hit pause now. Okay, let's see how you did. So I start by finding the area of the bullseye, which has a radius of 4.5. So area equals pi r squared. Substitute in the 4.5. 4.5 squared is 20.25. And then approximate with your pi. So we get that the bullseye is approximately 63.59 inches squared. So then to find the area of the 7-point region, I got to start by finding the radius. And the radius is going to be the 7.5 plus the 6.25. So I have a radius now that I'm working with of 9.125. And again, this goes back to that same idea of the pond and the walk problem, where there's that whole thing minus the bullseye. And we find out that the area is approximately 197.87 inches squared. Again, subtracting the bullseye out will give us just the 7-point region. Then we needed to find the area of the entire target. So I have to add up all of those rings. So I have 4 rings that are 6.25 inches each, and then the bullseye, which is a 4.5. So that gives me a radius of 23 inches. From there, I can put it into my area formula, area equals pi r squared. There's my 23, and I get is approximately 1,661.06 inches squared. For part D, it says the probability of hitting a bullseye on a random shot that hits the target is the probability of bullseye equals the area of the bullseye over the area of the entire target. So we want to know what's the percent that this could actually happen. So I'm going to start with the probability of the bullseye. And my bullseye, I had the probability or the area of 20.25 pi. Notice I went back to my exact answer so that my percent is not as far off. And then the entire bullseye, or the entire target, is 529 pi. Now those pi's cancel out and we can divide these out. And so as a percent, we get about 3.83%. So randomly, if you hit somewhere on the board, you have about a 3.83% chance of hitting the bullseye. All right, now we've covered all of the 6.3C lesson. You're ready to tackle that homework.